seminar. Today my talk is my first time to give a talk which has a more optimization flavor, and I learned a lot of optimization from my collaborator Dominik Stöger. He's now at the KU Ingolstadt, but he was a former postdoc at USC working with Maddie. So we're all like USC, it's a USC product. Okay. So when I say matrix sensing, it belongs to a big class of a problem in, let's say, signal processing. Nowadays we call it data science, or but it has always a similar flavor. You have some unknown structure which is have low complexity. Usually we can imagine it's a low rank matrix or sparse vector or even low rank tensor, and you have access to some measurement. Right? You don't have direct access to unknown signal, but you can have some noisy estimate of this. And the goal is to, based on this few measurement, you want to recover this unknown low rank structure with efficient algorithm. Okay. One popular example is matrix completion. In this case, you observe a movie rating matrix where the row could be the users and column could be movie. And the entries of this matrix is the rating of from the user. And the goal to do matrix completion in this context is to do some sort of recommendation, right? Based on some user's history, you want to recommend what is the next movie for the user to view. And you can make it possible because the assumption is user's preference can be explained by some finite many or very low parameters, right? The key factors of the user's preference might be depends on the age, occupation, and the movie's general, and so on. So this is approximately a low rank matrix. And based on some partial measurement, you should be able to recover the original ground truth if you have certain reasonable assumption. And there are many other problems has a similar flavor. For example, matrix sensing is a question where you have a low rank matrix and you do some linear measurement. And based on the linear measurement, you can create an optimization procedure to recover. Okay. Phase retrieval is a similar topic, a robust PCA, blended convolution. Also, like community detection in the network, you observe some very few connections between users and you want to recover the community assignment. So those are questions with a similar flavor. And today we will make it in a general problem setting, then we'll make our setting more concrete later. So you have a collection of linear measurement, which is a matrix, the ground truth matrix X star, and AI is some measurement matrix. And you observe some linear measurement, which is the inner product between AI and X star under the Frobenius norm. So you can write it as a trace of AI times Xi. Okay. And based on this measurements, in our case, you can think about all the AI are Gaussian matrices. And you can write it in a compact form where you have operators from a collection of, like say, symmetric D by D matrices to a vector Rn. And that's the vector you get from each measurement. And our setting, you have a low rank matrix X star with certain rank. And the goal is to estimate this unknown low rank matrix based on IID samples Y1 to Yn. In the matrix completion case, this AI could be some rank 1 or a very sparse matrix, right? Indicating what entry is 1, other parts are 0. And in our case, we'll work with a Gaussian matrix. And a typical approach to study this problem is called convex optimization. You can do some sort of a numerical nuclear norm minimization, right? So you minimize over a matrix class the sum of all the singular value with the constraint of this linear measurements. So if you have a convex problem, there are strong theoretical guarantees to show that if the sample size, the number of measurement is at the order of R times D, then with high probability, you are able to recover the ground truth with the efficient algorithm. And this R times D is pretty much the number of parameters you want to estimate, right? Because we have a low rank matrix and you have rank R times D is pretty much all the parameters you are trying to recover. But it is computational expensive, not in the like exponential running time sense. It's a polynomial time algorithm, but you are working with at least the D square many variables.
How do you solve this?
All right.
How do you solve this usually?
You can still you can approximately solve it use some integral point method. And there's another approach to study this type of question, is closer to the kind of a classical machine nowadays common template for machine learning. You create a loss function that measures the arrow between yi and the ai uv transpose. So uv transpose is the answer you are coming up with, and you minimize this loss function by doing some gradient descent algorithm. So it's a very, you can think about this as an empirical loss, and you minimize the empirical loss based on this observation. This will be computationally faster because now we are just looking for matrix factorization. So U and V are D times R matrices. They are not D by D. So you only work with roughly R times D many parameters. But however, in the literature, these theoretical guarantees for the convergence of those gradient-based algorithms, usually you need roughly R squared times D many samples. So here, the rank dependence is not optimal compared to the minimum information you need.
So this I is the true rank, or it's
the true rank. Yeah, we're
if
not
I use the over-parameterized rank.
Yes, then you that will be different. Yes, and you can change this over-parameterized rank.
Yes.
Then I think the sample complexity will not be this one.
Then algorithmically, the optimization landscape will
be better.
Yeah, right.
Yeah, yeah.
So you will talk about the algorithmic kind of convergence issues, or just the sample complexity?
We'll do algorithmic convergence, but not in the over-parameterized setting. Or just we assume the R is known.
Okay.
Okay. So yes, so this R squared dependence in the gradient-based algorithm is everywhere. You can see in many different matrix models. So matrix sensing we mentioned before, and matrix completion. You also have this issue with R squared dependence, even worse than R squared. Also, you can see it from blind deconvolution, demixing, and here you have this over-parameterized model where instead of trying to minimize the empirical loss, where you have a UV transpose the matrix, you over-parameterize it to be a R star matrix, where the R star is greater than R. I think that maybe 2 weeks ago there's a talk on this. Sorry, I missed it. Yeah, so this is also a very popular topic to study, because when you increase the parameter space, the landscape of the optimization problem can be better, and you have a better convergence guarantee. Also, you can study rank 1 measurement matrices. Instead of taking the measurement from a full Gaussian matrix, you take a rank 1 Gaussian vector tensor itself. So this talk, we want to understand, can we get the recovered guarantee when the sample complexity depends linearly on R? So another way to say it, is this really the truth of this algorithm? The algorithm really need R squared, or is this mostly a proof technique issue? So now we want to look at the simplest setting and trying to improve this sample complexity dependence. Okay. The simplest setting we have is similarly, you have the sample yi is coming from the linear measurement x star inner product with AI. And this AI, we assume it is a symmetric Gaussian matrix with the diagonal entry with a standard Gaussian n0, 1, and off diagonal has a variance 1/2. So this is known as the Gaussian orthogonal ensemble in random matrix theory. So it has some nice orthogonal invariant property. And now we assume the ground truth is also symmetric, positive, definite with rank R. And for ease of notation, we have the condition number, which is the ratio between the largest singular value and the least singular values. Okay, so this is our setting. So we strongly rely on this Gaussian assumption. I will comment on that later. Okay, and we're not inventing new algorithm. We are just analyzing a classical algorithm with a two-stage approach. First step, you do some spectral initialization. So based on the measurement, you can construct a matrix that's like in expectation, this will recover the ground truth. And you have this measurement matrix, you can find the closest rank R matrix as the first approximation. This is the truncated rank R SVD of this measurement you get. And from there, we have an initial guess of the ground truth. And now, so the intuition here is if you have enough sample size, you would expect this sample version of this random matrix will concentrate around the ground truth X star. And this can be proved pretty standard by using matrix Bernstein inequality or some epsilon network. And after that, we look at this objective function, which we have one argument, it is U, which is a D by R low rank matrix. And you try to take gradient descent with respect to this loss. And because we have a matrix structure, you can find a gradient explicitly, which has a very nice form.
So question, so original, the objective function would be like the Euclidean norm of this of the X star, right?
Yeah, that's the convex approach.
So
now we take the empirical loss function and you take gradient. So this is a standard two-stage algorithm, and there's a step size mu you need to take. Okay, so no, we're not inventing new algorithm. We're just trying to understand this algorithm with a better competitive bound. So why we want to use this two-stage approach? Because you know, in many non-convex optimization, there are many bad local minimums, right? But if you do a spectral initialization, it can avoid some minimum, local minimum that are far away from the ground truth. So the spectral initialization will give you a pretty good approximation to the ground truth. Then the gradient descent intuitively will just get trapped in this basin of attraction and converge globally to the ground truth if the sample size is big enough. So
how large the neighborhood of the initialization is needed for this two-stage algorithm?
So for us, you can prove a concentration estimate at the beginning, so that depending on how big the sample is, you can estimate how far it is from the ground truth.
Yeah, what is the usual order for the problem size?
For us, we just need for us, we need order 1, little o1, something like.
For the Gaussian ensemble, right? So
Gaussian,
real Gaussian
Yes.
ensemble, right?
So we need a sample size to be at least d times r, so that the initial error is of order arbitrarily small order. Yeah.
Just to go back for just 1 second, we'll do the initialization again. Okay. Okay.
So this two-step procedure, you start with a spectral initialization that gives you a good approximation. Then this gradient descent step, you can think about it as a local refinement. It gets closer to the ground truth. And this convergence rate, we have a quadraticization. Usually you can prove a linear
so within
convergence
this
rate.
basin of attraction, is that the typical landscape looks like this, or it's more kind of a curved, like you have local strong convexity within the neighborhood, or
I mean,
it's,
isn't this the point of the talk, to talk about how the spectral initialization is then followed up by gradient descent? I think you'll get to it.
Sorry. So we didn't try to characterize the landscape, like how many local minimum or the property of a local minimum. We just prove a convergence result. That's even stronger than the landscape analysis. Okay, so let me go to our result. So when we talk about recovering this low rank structure X star, we want to recover this the SVD, right, essentially. So the U star is the D by R matrix that gives you the factorization. And there's ambiguity because I can always rotate this U matrix to get the same X star. So when we measure the progress you make, the distance between the ground truth and the UT should taking over the subspace distance. So we should take a rotation matrix that's minimized over all the rotation, and you look at the distance between UT and U star. Okay, and our result is that assume we have the Gaussian measurement with sample size that's linear in R, but there's a kappa square dependence on the condition number, and the step size is have a lower bound, which is very mild. The lower bound has an exponential dependence on D, and the upper bound depends on the condition number and the spectral norm of X star. Then you can show that the distance between the T-step iterates and the ground truth is upper bounded by, this is like a linear convergence rate with exponent T. And this T can hold for all T greater than or equal to 0. And usually in a probability statement, this is doesn't seem true, right? Because usually we need an upper bound on the iterates. This is because there are
0 starts from the spectral, right?
Yes, spectral starting from the spectral initialization, and for all T greater than or equal to 0, this would hold.
Okay.
Essentially, to prove this kind of statement, you need a two stage. There's a one stage where this holds with high probability. So the probability statement well depends on how much iterates you have, right? I cannot let the probability phase run too long. So that's why we need a lower bound here to make sure that I need not too many steps to enter into a good neighborhood. And once you enter the good neighborhood, this convergence starts to hold deterministically. That's why I can bridge the stochastic part and the deterministic stage.
This is called constant step size, right?
Yeah, this is the constant step size.
About a new step size setting. Decreasing the step size.
You would like to have a constant step size, right? If you have a decreasing step size, you will make a slower convergence.
So you don't expect.
But I don't allow this step size to be very small. Otherwise, I need to take a union bound over the step.
Yeah, in practice, you decrease the step size, right? So.
Yeah. I mean, it depends on the problem, I think.
And also the condition number, especially the smallest singular value appears in the bound. Would you expect to improve with the second order methods?
Yeah, that's a good question. We didn't try to do a second method, and I don't think this is optimum, but we don't know how to.
Yeah, I mean, improving beyond this linear rates, you know.
You mean second order method?
Yeah, without
even accelerate
something. Yeah.
Okay. Yeah, that's we haven't looked at it.
Maybe on that same topic, the second order, at the very beginning, you talked about the d-squared dependence.
Mm-hmm.
Do you start facing the algorithm speed issues if you start doing quadratic like that? Because that's sort of the trade-off, right? You're looking at the gradient descent is the faster algorithm, but maybe is also good enough usually.
So second order method, you have a faster convergence rate. That's
if you can get it for free, right? Maybe the Hessian is harder to get. Do you think it's the same issues as the beginning or no?
It's an iteration complexity.
Okay, yeah, this is not all what we're trying to optimize here. Yeah, the focus here is to get the linear rank dependence.
Yes. First. So the sigma minimum is the minimum eigenvalue.
Minimum singular value of X star.
Minimum what?
Singular value. That's also eigenvalue because we're looking at the positive semidefinite matrix.
I'm a little curious about that because if there's suppose the real rank is R, but because some error it becomes R+1, the minimum one will be close to zero. I'm just puzzled about that.
Yeah, and then the condition number will blow up, right? The condition number is largest divided by the smallest, yes. If in this case, the sample size also blows up. So those are the cases where.
So what I mean is if you say because some error is just from R to R plus one. I'm just thinking of the minimum, sigma minimum might be quite sensitive to the data error. That's my.
Yeah, so we assume the matrix has rank R, and the least singular value is R, sigma R. You are worried about the gap between R and R plus one. That's
not really the gap. It's kind of what if.
So your model is noisy setting, right? So right now the sensing measurement is noiseless, right? So do you have stability here?
Yeah, we this is our first step to this question. So yes, there are a lot of follow-up things you can consider. Yeah, if you have a noisy perturbation, then this could change the least singular value. Yeah. Okay.
Sorry.
She has a question.
Yeah, sure.
Oh, yes. I remember there's an assumption about the sensing matrix.
Yeah.
Yeah, what is the role of the assumption in establishing this?
Oh, we need this Gaussian assumption. I will mention it. That's like a key input in the proof
And
argument.
also, I remember the sensing matrix need to have independent entries, right?
Yeah.
Is that necessary?
For Gaussian.
Yes.
Yeah, you can also ask like a structured sensing matrix, like a circular matrix. Yes, and like a rank one measurement. That's also interesting to consider. Yes, you could have a measurement matrix with dependent entries. Yeah.
Sorry. So are you using like the local convexity conditions implicitly in proving this theory, like the linear convergence?
Local convexity. No, we don't.
Okay.
So yes, we have several problem has been mentioned by the audience, right? So first is this quadratic depends on condition number optimum. We don't know it yet. The step size, can we make it more flexible? This is also interesting to consider. And so going beyond Gaussian measurement, what if you want to do sub-Gaussian entries with independence or even correlated entries? That's also interesting to consider. I just also want to mention that even in this matrix completion setting, even for a convex method, there's an extra log R dependence that's not being eliminated yet. So even for convex method, this is not sharp enough. And for non-convex method, there's a rank dependent that's R to the Q. Yeah.
Do they refer to noiseless case?
Noiseless, yeah. It's all noiseless case. And yeah, also if we go beyond the symmetric positive definite case, if you have an asymmetric ground truth, this will be different. And if we do random initialization, that's also an issue you have to address. Now we have a spectral initialization, which makes the problem kind of a local at the beginning. If you have random initialization, this is a different question. So let me go to the proof idea, and then so we'll basically look at how the R-squared dependence appear. So usually the proof goes in this way. You need to control the gradient at each step, and the gradient of this loss function can be decomposed as the expected gradient over all the randomness of the measurement plus the fluctuation term. That's the true gradient minus expectation. Okay. And you want to control this fluctuation term to have small spectral norm. And the key quantity to control is something like this. This fluctuation is bounded by some constant times this delta t. And delta t is the distance at time t, how far you are from the ground truth. Okay, so you usually need to control, in many cases, you need to control this quantity. And the difficulty here is if delta t is just some matrix independent of this measurement AI, you can prove it by some standard concentration bound. However, now we have a stochastic process, so the delta t will depend on those measurement matrix in a nonlinear way. You cannot easily decouple delta t and AI. So you cannot apply some concentration inequality easily. But on the other hand, we can try to do a uniform concentration bound, right? I can ignore that this is a gradient trajectory. If I have a control over all possible rank 2R matrices, right? This, because the delta t is a difference between two rank R matrices. So you can measure it by a rank 2R matrix. And this is a bigger parameter space. And you can try to prove some uniform concentration bound over this parameter space. And if you do that, there's an R squared term up here, right? Because we want to have the right-hand side to be of order 1, and your M must be in quadratic in R. So this bound will apply for all iterates because I just enlarge my parameter space and I don't care about the dependence of my iterates. And you can do that because here you see this is like a quadratic process in Gaussian matrices. So you can use classical empirical process theory and like restrict isometry property in the signal processing literature. For example, the paper by Kramer, Melders, and Rahut, you can get this type of concentration result. And if you use that, you see the dependencies are squared. Okay, so here's the issue. And we might ask, can we really improve this bound? Right? Maybe this bound is loose, we can have a sharper concentration bound. And in fact, this is not true. So, okay, there are too much computation. Maybe let's quickly go through it. So we want to have a control over all the rank 2R matrices with operator on 1. But what you can do is, this is the variation formula of the spectral norm. You minimize. You also maximize over the unit sphere. And I can pick a particular subspace of my parameters, which is orthogonal to the first vector, the EI. And that gives you a lower bound in a way that's depend on a top singular value of a matrix B, which has this form. This matrix B has EI, so this is a Gaussian scalar times each measurement matrix AI. Okay, so this quantity is lower bounded by the top 2R singular values. And by some standard random matrix technique, we can show that if you have a control over a singular value of this B matrix, you get a lower bound that's also R squared dependence. So if you try to just make it sharper, it doesn't work. There's some bad case of the Z to make this bound tight. So the issue really is that the parameter space is too large, right? If you work with all the rank R matrices bounded for Frobenius norm, this covering number will have a growth rate that depends on this R. Okay. And this R dependence will be translated into the R squared dependence if you just keep track of everything. And what's the issue here? This matrix Z, if you go back, is actually relevant to this B matrix. And you see this B matrix has a strong dependence on EI and EI transpose. So this is like a specific entry of this measurement matrix. So if you have a bad example Z, which is strongly depends on a particular entry of this measurement matrix, that gives you a lower bound. But in reality, what we have here is, yes, we have a big parameter space T, but you start with U0, which is the spectral initialization, and this gradient trajectory will take you to the ground truth U star, and they will only pass through a subspace or certain region of my big parameter space. So we only need to control this trajectory, but not the entire space. If you just do the uniform concentration bound, you basically pay the entropy cost of all parameters that even includes some bad corners of the parameter space. For example, this the EI transpose. You can imagine this is some bad corner in this parameter space. So in fact, we would imagine that this gradient descent iterate should only depend weakly on some specific projection direction of my measurement. So this VV transpose, if you think about as a generalized entry of my matrix, this rank 1 projection should have a very mild contribute to my iterates for each V. Okay, so this is our observation, and we want to make this intuition rigorous. In fact, this is, I think, a quite common topic, a common situation when you do deep learning theory, or not deep learning, but deep learning theory. There's always this issue, right? You have a model that's over-parameterized. So, for example, you can train train a gradient descent on the loss function, and there are many parameters to make a loss 0. So, for over-parameterized model, you have many candidates to like local minimum, but standard or uniform convergence bound will take into account to this big parameter space, and that will usually depends on the covering number or the VC dimension of the parameter space. However, those type of bound will not tightly depend on specific algorithm. And quite often, the current active research in deep learning theory is to show some sort of implicit regularization. So if you run certain algorithm, a gradient descent algorithm, it will this gradient step will prefer certain type of parameters. For example, minimal norm interpolator, different type of minimal norm in different sense. And that's one of the key observation in practice, and one of the key ingredient to prove many tight results. One particular example I like to share is this. There's a nice paper about linear regression. So linear regression, if you have an over-parameterized linear regression model, you can always talk about the performance generalization error on minimal norm interpolator. In that case, if you draw a ball around the minimal norm interpolator, you can show a local uniform convergence bound. So instead of looking like a big parameter space, but if you restrict to a smaller subspace, you can still hope for some local uniform convergence. And actually, our proof will have a similar flavor. But I want to mention that beyond matrix recovery setting, there are many problems. You have this kind of feature. Okay. So how do we make this intuition rigorous? So we want to have an algorithm specific control of the parameter space. And the key proof technique here is we do some sort of called a virtual sequence. In other contexts, it's called a leave-one out analysis, but now we are generalizing this idea of leave-one out. So the idea is we want to show the concentration bound along gradient trajectory by perturbing the measurement. It's like a trade-off between, I don't want to show the concentration over the parameter space. Instead, I want to show some robustness of my gradient trajectory. There's a trade-off between these two properties. So what do we do? Instead of leave one out, so the standard leave one out approach is you have a big matrix and you delete one row and a column and see how this deletion will affect your optimization. And that's also rooted in, like in physics, it's called cavity method. In the random matrix theory, it also has a different name. If you do resolvent, there's a way to delete a row and column, and you use some Woodbury identity to analyze things. So here, instead of doing a leave one out, we can take any unit vector and subtract a rank one projection of this unit vector. This is a generalization of the leave one out. I can perturb my matrix in all kinds of directions. And the nice thing here is, because of I'm using the orthogonal Gaussian ensemble, if you subtract this rank one component, you get some independence, right? This AIW matrix will be independent from this rank one part. So instead of deleting entry, we subtract rank one projection. Now you do the same thing. Now this is my modified measurement. Now I have my modified observation. And now you can do the special initialization on this modified observation, and you run gradient descent on this modified initialization, and so on.
So this use the Gaussian structure here.
Yeah, we use the essential, we use the Gaussian structure. Okay, so we can imagine that you can perturb my measurement in all kinds of ways, but we don't need to do that. You can discretize the sphere. So that's the idea here. And what do we have? The property of the virtual sequence. For each this direction, this sequence will depend on AIW, which is the subtract, this measurement subtract the rank 1 projection. So this measurement will be independent of this specific entries, AI inner product of WW transpose. So you have a quick independence because of this very beautiful property of Gaussian independence. If you take a Gaussian vector and you project into an orthogonal subspace, the entries are independent. And now we hope that after this perturbation, we create a collection of virtual sequences, and they stay close to my true gradient sequence for all iterates. Right, so this is the picture here. We have a true sequence from U0 to U star, and you perturb it. It's like you're perturbing it to make a small ball around the initialization, and based on those small perturbation, we want them to run the same dynamics to create a sequence of balls around the trajectory that effectively give you a kind of a covering of my gradient trajectory, which is depending on the algorithm itself. So now we want to pay more attention to this region instead of looking at the entire parameters. Okay. And so the key property we have here is that if you discretize the unit sphere, you just take epsilon net, then when your measurement is more than r times d times kappa square, this deviation term, which we want to have a uniform control, is bounded by, this is the distance from the ground truth, plus another term, which is you want to control the uniform error over all virtual sequences. So this is the quantity you need to control. And here you can use this independence between the virtual sequence delta W and this specific entry to get this type of bound. Okay. And the key observation here is before we're working with this big parameter space T, it has a covering number of order constant to some power depending on R, and that's the entropy you need to pay. But now the only union bound you do is over the sphere, which has no dependence on the rank.
It's because you project to rank 1, right?
Yes. But the extra thing you need to show is the robustness of this gradient sequence under rank 1 perturbation. Right, so this is but now we use the structure of this problem instead of just pessimistically search over all the parameter space. And you can believe this is true at initialization because what we do is just a rank 1 perturbation. So by classical Davis-Kahan analysis, you should imagine they are close, and you can show they are truly close. And then from t equals 0 to 1, 2, 3, and so on, you need to do some induction proof to measure different errors, but that's kind of mostly a deterministic control, not a stochastic control. So by showing the robustness, you avoid paying the big entropy cost to a small entropy cost. That's the insight here. All right. So let me summarize what we have. So the message here is oftentimes if you want to do some uniform concentration analysis, this can be leads to overly pessimistic results because oftentimes you have a big parameter space, but your algorithm will only go through a specific region of the parameter space. So the gradient descent iterates often enjoy additional properties where you can exploit via virtual sequences. Okay, and this has been this idea of perturbing the sequence has been used in many other contexts, but usually it's called a Liouvin out analysis. But they can do it for more general measurements. Now we need to this Gaussian measurement to create more. Right? So this. If you just delete one row and one column, at the most you create n many virtual sequences. But now if we do the rank 1 projection, we create exponentially many sequences that gives you a nice cover along the trajectory. So the main conceptual novelty is we leave one Gaussian projection out instead of deleting one row and column. And combining this virtual sequence, you create a epsilon net along the trajectory, which is algorithmic dependent. Okay, I think this observation or this proof technique might be useful for other settings. For example, we mentioned the rank 1 measurement or matrix completion. So those are the questions I'm excited to explore more. Okay, thank you for your attention.
Any questions?
So I'm interested in the noisy case. Yes, so here the model is that